Good morning, class. Welcome to my first official online lecture. This is Dr. Jordan. We're doing Math 12, Section 4.5, Solving Exponential and Logarithmic Equations, Part 1. We'll start with the first type, which I will call the easy type. That's if both sides have the same base. Simple example would be something like 10 to the x power equals 1 million. We can clearly see that a million is already a power of 10. So we can simply rewrite a million as 10 to the 6th power. Yeah, I know, I already practiced this, but you might just do it in your head. 10 times 10 times 10 times 10 times 10 times 10. If you have 6 tens, that's going to be clearly 1 million. So you might not get it on your first guess, but you definitely will get it on your last guess. So if 10 to the x is equal to 10 to the 6th, then clearly, I will say clearly x is equal to 6. We will refer to this as the same base property. And I will continue to use it throughout the lecture. So the same base property symbolically can be written something like this. If a to the x is equal to a to the y, then x must be equal to y. Now, until I buy a larger whiteboard, we're going to be doing one example at a time. So feel free to rewind the video if I go too fast, or if you need to watch it again. These are not live streamed, so you can watch this video as many times as you like. Let's try another example. 2 to the x is equal to 0.25. Oops. Sorry about that. I've been practicing for a week, guys, but I'm still a little rusty. So 2 to the x is 0.25. You might recognize this immediately as 1/4. Hopefully you do. That's 1/4. And so 1/4 is what? 1 over 2 squared, which is the same as 2 to the negative 2 power. So we can rewrite this as 2 to the negative 2 power. Again, we have our same base property here. So the bases are the same. Therefore, x is equal to negative 2. Maybe I could squeeze another one on here while we're at it. Example 3. 3 to the x minus 2 is equal to 1/3 to the 2x minus 8. So you see, the bases are similar, but not exactly the same yet. So we might need a little bit of manipulation in order to make these bases come out to be the same. So what can we do? Well, we can use a little mental math here. 1/3 is 3 to the negative 1 power. So we do have the same base here. We just need to add in an additional step. So we got 3 to the x minus 1 is equal to 3 to the negative 1. Use parentheses or you'll regret it. to the 2x minus 8 power. And so now it's just a matter of combining these exponents. Make sure you use the distributive property. So you have negative 2x plus 8 is the new power. So this is where the same base property doesn't quite give you the answer immediately, but it does give you a much simpler equation. You get x minus 1 is equal to negative 2x plus 8. And now you can solve this relatively simply. Ordinary linear equation. So let's go ahead and add 2x to both sides. I'm probably getting off the screen now, so let's come over here. So I've got 3x minus 1 is equal to 8. I think you can take it from here. 3x would then be equal to 9, or x would be equal to 3. So that would be my solution. X is equal to 3. At this time, I would typically ask, are there any questions? I will be doing my office hours on Zoom later today, 11 o'clock Pacific time, my normal office hours. So please check your Canvas link and come to the Zoom office hours if you have any individual questions. Maybe we should do one more, and then we'll move on to the type that are not so straightforward. So example 4. E to the 2x minus 1 is equal to 1 over e squared. Now, clearly these have the same base. There's no trickery going on here. So all we're going to do is rewrite the right-hand side as e to the negative 2 power. We're going to invoke our same base property. Sometimes it's nice to just put it on the side. Should probably come up with an abbreviation for it. That way, if you're looking back on this, you know how I got from this step to this step. One thing that you should pay attention to with the same base property is you never go back. So, maybe, in some procedures, you do something, and then later on, you'll go back and undo what you did. This is a one-way street. So you invoke the same base property, and that's it. The old equation is gone, and now you just have this new equation. So we're going to add 1 to both sides. Get 2x equals negative 1, and then divide both sides by 2. Let's get rid of our last one here. Now we have x is equal to negative 1/2. Okay. So they're going to get a little tougher. We can't assume that this is going to happen all the time, where we're just going to get problems that are basically custom made that have the same base. The real world doesn't quite work like that, all right? So we're going to end up having to solve problems that have different bases. So the next few examples are involving exponential equations that do not have the same base. Say goodbye. I'm going to go to Staples, if they're open today, and buy a larger whiteboard, maybe a bigger tripod. We'll see how that works for now. So, all right, example 5. So suppose you have something like 5 to the x power is 20. Yeah, I know, 20 is 5 times 4, but 20 is not an exact power of 5, at least not one that I learned growing up. 5 times 5 is 25. You skip right by 20. 5 to the first power is 5. So, you can come over here and experiment and say, well, is there any way that I could get 20? Yeah, somewhere in the middle here, somewhere between 5 to the first power and 5 to the second power would be, 5 to the 1 point something power would equal 20. So I do get some sort of an idea of where my solution would lie. I know it has to be bigger than 1, And I know it has to be less than 2, but unless you have a really good mental math power that I never learned growing up, we're going to have to use logarithms, which is kind of the whole reason why we've been studying this for the last couple weeks before the crisis. So you can use any log that you like. We have the natural log, we have the common log, and we have the log that's given in the base. For this particular example, let's go ahead and use the log base 5. So we're going to take log base 5 of both sides of the equation. So we're treating a logarithm sort of like we would treat a principal square root in a previous chapter. We wanted to solve an exponential or a polynomial equation. We would just, second degree polynomial, we would take the square root of both sides. Well, we can't necessarily take the square root here, but we can take the log of both sides using the base 5 and a property of logarithms that we learned before, where the exponent can drop outside of the parentheses and drop down to the front to become the coefficient of the logarithm. Refer to lecture 4.4 when we learned about the properties of logarithms. Okay, and one of the original, I think it was called property number 1, or maybe it was property number 2 of logarithms, was log base. Any base of the same argument is going to be 1. So this is x times 1 is log base 5 of 20. Clearly x times 1 is just x. And so there's our solution. Now this is the exact value. So if I asked for the exact value, it's log base 5 of 20. However, you might want to do an approximation. Use your calculator. So one of the final properties that we discovered in the previous section was the change of base property. The change of base property allows us to use an ordinary calculator like this to calculate the exact value of this. Now, if you have a much fancier calculator than the one I have, and I just have a basic TI here. I mean, they have fancier calculators. You want to spend $100 or something, you can get a calculator that'll just calculate this log without having to do what I'm about to do. So if you happen to be one of those students that has one of those, that's fine. You're lucky. What we're going to do is we're going to use a calculator. I'm just going to use the common log of 20 divided by the common log of 5. Or if you prefer, you can do the ln of 20 divided by the ln of 5. Don't mix them. So if you're going to do common log for the numerator and the denominator. If you're going to do natural log, then do that as well. Let's see. So we got 20. I'm going with the first one, common log divided by 5. Common log equals 1.86. And give me as many decimals as needed. I actually use the common log for my solution, but it does not matter. You're going to get the same result either way. If you'd like to see that, I can show you. I'll try natural log of 20 divided by natural log of 5, and I still get the same approximate value, 1.86135. Okay, round as directed. It really depends on what we're doing. You've heard me say this before. Right now, just get me the right answer. Follow the directions as needed. Okay. So that's it for example 5. I wish I could ask you how it's going. I guess I'll find out later in office hours if you have any questions. So. Example 6. Six to the 2x minus 3 is equal to 32. Again, we have an equation that it's nearly impossible, at least with mental math, to tell me what power or what exponent you would raise 6 to in order to exactly get 32. And if that was a 36 instead of a 32, then we could revert back to the same base property that we saw earlier, but I'm just going to assume that it cannot be done, not at least by initial inspection, so we're going to use a logarithm. Now, one thing you might have noticed in the last example is when I use log base 6, well, that makes the left-hand side come out very nicely, right? But then the right-hand side, you have to then resolve that later in the problem. So one strategy is just to use either the natural log or the common log right from the get-go. You know, why wait? If you know you're going to do it anyway at the end, why don't we just get it over with? Let's just rip it off now. Now, the only price you pay for doing it this way is you're not going to get the nice cancellation that we had, because now I'm using a common log. This is implied to be base 10. That's what we call the common log. And so that applies to both of these logarithms here. So the 6 and the 10 do not have the same base, so we are not going to get that nice cancellation property. However, we will still be able to invoke the exponent property. You can always use the exponent property, bringing the exponent down to the front and writing it as a coefficient. Now, log 6 is a number, right? If you like, you can see it on the calculator. Log 6 is a number. It's 0.77815, blah, 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 blah. Now, if I put this decimal into my equation now, I have to write that decimal down over and over and over and over again every time I want to move to the next line. Why don't I just hang on to that? In my head, I know that this represents 0.718, or 778, excuse me, so I can just distribute it like an ordinary constant. Now, I know last time we met in class, I had told you, never distribute a logarithm. But what I actually said was never distribute just the symbol or the word log. You can distribute it if you bring its argument with you. So log 6 you can distribute because log 6 is a real number. If you tried to distribute just the symbols log and sort of separating them from their argument, then that would be illegal. So that's what I was referring to in class a couple weeks ago when I said never to do that. So now you need to resolve this equation, get everything onto the other side except your x. I'm just going to move my 3 log 6 onto the right-hand side. And that brings me to 2x log 6 equals log 32 plus 3 log 6. Finally, I'm going to divide both sides by 2 log 6 These are all products here, so this is like a factorization here, so I can easily divide off the common factors and isolating my x. So now I've got x is equal to all of this. I'll just write it one more time. Looks like I've got room for it. It's quite an exotic solution. Not easy to write. Be very careful. Everything is... Use lots of parentheses if you're typing this answer onto Canvas. If we had to approximate this, I would just do it very, very carefully. Looks like I'm all out of board space, so we'll have to save that for another example. Questions? Oh yeah, you can't ask. How many more we got to go? This is just part one of the lecture. So we'll get through a few more of these. Okay, example 7, coming right up. About e to the 3x equals 23. So e is nice because we have a button for e. We have the ln here, so we're clearly going to use the ln. Each problem kind of tells you what it needs if you read it carefully before jumping in, you know. Read it and look at what it's made out of and then decide what the proper treatment is. Now, the nice thing about e, it's kind of like 10, which we have the logarithm for it already. Well, it's actually nothing like 10, but in the sense of a logarithm, it behaves in the same way that a base 10 would behave. When I bring down this 3x, then I have ln of e, just like we did in our first example with the 10. Ln of e is 1, just like log of 10 is 1. Some people just cancel that out instead of actually writing a 1 like I did last time. That's a probably more efficient way to get to the nut of what you're trying to, the seed of the nut. Okay. So you see how that happens? That this ln of e just becomes 1, so you have 1 times 3x. And then now we just divide by 3. And so this is my exact solution. And if need be, we can approximate this by rounding to, let's do 4 decimal places this time. So we have 23 ln, so that's 3.13549 divided by 3. And that gives us 1.04516. Rounded to 4 decimal places would be 0452. You can all see that. Okay, good. So how's it going? We're coming up on 24 minutes. I don't know if time really matters at this point, but I'm going for completion. I'm trying to do as many examples as I possibly can in this first run. I really do appreciate all your patience. Should we try another one? Do I hear a yes? Okay. Let's try another one. I forgot what that was. Was that example 6 or example 7? It's a lot like class where I always forget what example I'm on. I like to just call it example next. All right, next example. So let's pick a logarithm to use. Maybe natural log? I like natural log. I like to give you the idea that you can really choose the logarithm that you use. This problem has 3 natural choices. One is the natural logarithm, one would be the common logarithm, or you could go with log 13, which is what the problem was originally set up as. The only consequence to choosing log 13 is later on in the problem, you're going to have to then recalculate what log 13 is. And if you have the calculator that I have, that is it's easier said than done. If you own a fancy calculator, then you could just do log 13 and be 1 step ahead of the game there. It's one of the reasons why people buy the fancier calculators. So remember, if the log base does not match the base of the exponent of the exponential, then these will not cancel. They will not become 1. So the only way this would become 1 is if it was an ln of e, or if it was a log of 10, log base 10 of 10, or if you were using log base 13, then these would in fact cancel. Now what would be the price? The price would show up on this side. If you canceled the 13 on this side, well then on this side you would still have a log base 13 that would eventually have to be resolved. Okay. Let's get rid of these negatives, this negative sign and this 5 first. Those things are going to cause us some problems. So let's multiply both sides by negative 5. Negative 5. And that will cancel these 5s and these negatives. And we'll now have negative 5 ln of 15 on this side. Okay. And you can divide both sides by ln of 13. And there's your solution. All right. So a little note before we move on away from this problem. There are other correct answers for the exact form. You could have used the common log. And this story would have sounded exactly like the same story, but with a different main character. It would be the common log. That would also be a correct answer. These are identical. They give you the same result. We can see that using our calculator in a minute. I'm saving this space up here. Or at the very beginning, if you would have just used the base that you were given, you used base 13, it would look a little neater. It's a little bit cleaner to write. So some people prefer this because it's just one line, doesn't require a denominator. But the price you pay for getting rid of your common log or your natural log and reverting to the intended base of this problem, which is 13, is now you can't do it on my old-fashioned TI-30 calculator. You would need a slightly more expensive calculator to do that. Okay. Either way, all 3 answers should give the same approximate value. All right, so let's see what we get. Let's see. I do my logarithms first and multiply by -5 last, because especially with this type of calculator. So we're going to go log of 15 divided by log of 13. Okay, so that's just the quotient of the two logarithms here. And now I'm going to multiply that by -5. And my answer is -5.2789. It actually keeps going. So to round this to 4 decimal places, 90. I know that happens sometimes. If the 6th is 4 places, 4 decimal places. If the 5th decimal place is larger than 5, then we round. I hate telling you guys this, but you already know. Then you round the 9 up to a 10. That becomes a 0, and then that rounds the 8 up to a 9. And yes, you have to put that last 0. Otherwise, the computer will think you only did 3 decimal places instead of 4. Okay, I'm going to wrap part 1 up pretty soon and see if I can upload this to my YouTube channel today. Hopefully you guys can get it before too long. I'll be checking to see how many of you are viewing these. So we have one more example, and then part 1 will be concluded. This is a 2-part lecture, so stay tuned for part 2 coming very soon. All right, here we go. You can always rewind it, because that's the good thing about all of this. Last example. This type of problem is called a quadratic form. I don't know if you recognize it, but it has the same form as a quadratic equation. I mean, so you can imagine that the e to the 2x is like a second power of some substitute variable. And the e to the x is the first power of that substitute variable. So u is sometimes called a sub, or a substitute. Substitute. So we're basically going to let e to the x equal u. And now we have a much simpler problem to solve. You guys probably hear me say this a lot. You don't solve complicated problems. You turn the complicated problem into an easier problem. So this is now much easier to solve. It's an ordinary quadratic. It's even a factorable quadratic. If you get desperate or if you get unlucky and you get one that's not factorable, then use the quadratic formula or one of the other methods that we learned, completing the square or something like that. Okay. And then you get u is equal to 6, and u is equal to 5. But remember, who is u? U is a substitute, so we're going to replace the substitute with e to the x. Now, I already kind of hear a question coming through the internet here. Do I have to substitute the u? No, you don't. If you see this early and you're like, well, that's like x squared and that's like x, and you just want to jump straight to the factored step using e and e to the x and e to the x, you certainly could skip all of this substituting and just go e to the x minus 6, e to the x minus 5. So showing you this method of substitution, I'm really planting a seed for something that's going to happen in the future. Probably will happen next semester in calculus. The concept of a substitute, and in particular a u substitute, is an important concept in calculus, mathematics in general. Okay? And then I also want to caution you, when you do this process, e to the x must always be greater than 0. So if you get something like, e to the x equals -5 or e to the x equals -6, stop. That solution is DNE. It doesn't mean the whole problem is DNE. It means just that particular piece of the problem does not exist. The solution would not exist. In this case, they are both positive. E to the x is 6, e to the x is 5. These are both positive, so we should proceed as normal. If they were both negative, if these both came out negative, I would stop right now, be done, DNE. If one of them was negative, I would throw out the one that's negative and keep the one that's positive. So we're just going to take the ln of both sides, and so we're going to have ln e to the x equals ln of 6. Here's a trick. We can just cancel the ln and the e and just say x is ln of 6. Parentheses, I think, are required on Canvas, but when you're writing this in paper, of course, it's not required that you have parentheses. So these are the two real solutions. All right, I hope that was helpful. If you do have any questions, check back later. Hopefully we'll have the Zoom office hours up and running by this afternoon, or by 11 o'clock around lunchtime. So just check in with me then. Okay. This is Dr. Jordan, signing out.